So chapter 5, the big idea here is the idea of the central limit theorem. So previously we've been running these sampling distributions by taking a given sample and reselecting from that sample to see what kind of variation we can find. We're resampling there with replacements. We get a lot of different variety that can happen. So this gives us an estimate of what other kinds of samples might be out there related to a population if we start with a good random sample that's representative. Turns out, interestingly, that all of these sampling distributions, or most of them, have the same shape. And this shape can be approximated by what's called a normal distribution, which is a mathematical equation. We don't really need the equation, but the big deal about a normal distribution is that it has this symmetric bell shape. So you can see I've outlined the sampling distribution in red here. A normal distribution is defined by its mean. In this case, when I'm looking at the graph, the center down here, it looks like I have a mean of 0. And the spread was given to me by stat key over here. That's called the standard error, and that's the standard deviation for the sampling distribution of this statistic. And so that is 0.395. So my standard error, which is the standard deviation, 0.395. And again, that is a standard deviation for the sampling distribution. So now we have a couple of techniques to run hypothesis tests, to do confidence intervals, and we're going to keep exploring these over the next couple of weeks. Let's look at an example. So there's a study that was done at a university about leniency in a disciplinary hearing for students that were accused of cheating, and whether the students were presented in an image as smiling or neutral. So the disciplinary board received their case file, and in the case file was a picture of them. 34 of the students, and they were randomly selected into these two groups. 34 had a picture of them with a smile, and 34 had a picture with a neutral expression. And then they came up with this leniency rating. So based on the offense and the type of discipline that could be issued, they had a rating, I think it was from 1 to 10, 0 to 10, for how lenient the disciplinary board was for each individual. And the question is, does smiling versus a neutral expression affect the leniency in the disciplinary hearing? Maybe if you have a smile, that changes the mood of the person that's judging you, and they might be more lenient toward you than if you had a neutral expression. So I've listed out the summary statistics here. We have a sample size of n equals 34 for the smiling people, and the average leniency rating for the people with smiles was 4.91. The 34 people who were presented with neutral expressions had a mean leniency rating of 4.12. And what we want to know, is there a difference, a significant difference here, or is there no difference on average? So when you subtract these two means, the smiling people's leniency minus the neutral people's leniency, you get 0.79. And one might wonder, well, it shouldn't matter whether you're smiling in your picture or not. It should depend on your offense, right? So this smiling versus neutral should have no effect on the discipline, is the null hypothesis. So I've stated that in a couple of different ways, that the average leniency rating for the smiling people should be the same for the average leniency rate. Oh, I totally messed that up. Those should be mu's. Anyone catch that? Eraser. That should be a mu. Right, null and alternative hypotheses are always addressing the population, not the sample. We use the sample to check to see what's going on. So that should be a mu. Oh, and I guess I don't need the bars either, do I? Sorry for that typo. Mu. All right, so back on with it. Ooh, bigger eraser. All right, so this is what my hypotheses could look like. So if they're equal, that means there's no difference. So average difference is 0, average difference in means. But I'm thinking maybe smiling will affect the outcome. And so the mean difference might be greater than 0, meaning the smiling people, they were treated more leniently than the people with neutral expressions. So next we need to look at the data to see if for these sample sizes of 34 and 34, is a difference of 0.79 close to 0 or far from 0? And you never know until you run some kind of test. So off the stat key we go. And so here I am in stat key. Okay, what are we doing? We are looking for a test for a difference in means. So over here, hypothesis test, and I have a difference in means. And here's the original data over there. We could explore it in the edit or show data table if we wanted to. We can see the smiling people had an average of 4.912 and the neutral people had an average of 4.118. And the difference in those means is expressed up here. And so what we want to do is run a sampling distribution. Now, one nice thing in StatKey is for a difference in means, we just assume that the difference is 0, that there's no difference, they're the same. So I don't have to worry about setting that. And you can see in the sampling distribution, it's hovering around 0, no difference, right? The difference equals 0. So that's my null hypothesis value down there. And let's say I got 7,000, that should be good enough. To get the p-value to find out if this difference is significant, then we have to run, in this case, a right tail test, because I'm looking at a greater than alternative. And I just replace that cutoff with mine. So we've done this a lot now. And so StatKey says, according to this simulation, we get a p-value of about 2.5%. And usual significance level is 5%. So this is under the usual significance level, which means this is far enough from 0 to say, huh, smiling looked like it matters when we assumed it didn't. Interesting. So I would reject the null hypothesis here that there's no difference and say, yeah, the difference seems to be greater than 0. That smiling does make one have a more lenient discipline for cheating infraction in the university. Now, I can also look at this with the theoretical normal distribution as long as I know the mean and the standard error of the distribution. So here my standard error is 0.398, a little different than the last time I run it, but close. So over to StatKey again. And this time I want to check out what the theoretical normal thinks. And every time we use a theoretical normal, we have to double check, do we have the right parameters, mean, standard deviation? I am checking a mean of 0. But my standard deviation is the standard error of the sampling distribution, which StatKey for that one thought it was 0.398. Let me double check that. Standard error, 0.398, yep. All right, so mean standard error is the standard deviation. And then it's pretty much similar to before now. I just right tail it and enter my sample statistic, which was 0.79. And StatKey says it's about 2.4%. So is it different than what the randomization test said? Yes, the randomization said it was 2.5%. But is it similar? 2.5% and 2.4% I think are relatively close to each other. Would it lead to the same conclusion? Well, they're both under 5%. So yeah, my conclusion is the same whether I run the theoretical distribution or the randomization distribution. And again, keep in mind, every time we run a randomization distribution, we're shuffling the cards again, and it's going to be a little bit different. So let's do 7,000 new samples of these 68 people, reshuffled, and check the right tail again, and the p-value for our data, which had a difference of 0.79, and this time I got 0.28. So there's going to be variation in the randomization distribution, but they're going to be close. Notice the standard error is a little bit different now too. It's 0.402. Is 0.2028, 2.8% similar to 2.5% or 2.4% at a significance level of 5%? The answer is yes, they are similar. They both lead to the same conclusion. So it looks like, according to this data, that smiling might lead to more leniency in the discipline if you were accused of cheating. Hope this helps. Take care. Do good math. Bye-bye.